Minimum. Maximum minimum problems. What we're trying to find here is we're trying to find when the slope equals 0. I'll give you an example. Let's have 100 meters of fence. Okay? And I want to maximize the area of a rectangle. Okay? So we're going to make some sort of rectangle. So there's one already constraint, is that we're going to make a rectangle. We're not going to make a circle. We're going to make some sort of rectangle. Now, I think we know that this is going to be a square, but I want to prove it to you. Okay? So our perimeter is 100 meters. There's one equation. And the other equation is the area. So that's the first thing we have to do in these types of problems. You have to write down the two equations that govern the problem. We already know that one of them is going to be a rectangle, which already sets a lot of things. So we know that the perimeter is equal to 2 times x plus 2 times y. 2 y's and 2 x's give me my perimeter, and that equals 100, always. So there's equation number 1. The second equation is going to be the area is equal to x times y. That's it. And what we want to do now is we want to maximize area. So we have 2 equations here, but we have 3 unknowns. We have x and y we don't know, and we also don't know what a is going to be. But we do know one other piece of information. And this is what I'm going to try to prove. So let's just try a couple of these. Let's try, I'm going to make up a little table here. Let's try x of 10. Okay, so if x is 10, then it's going to be 20, so I'll have 4, so y will be 40. Okay? And then the area will be those times it will be 400. Okay, that's the area. Let's try x equals 20. Okay, if x is equal to 20, so that's going to be 20. 20 is 40 total in the x. And then this one will be 30. Well, it'll be 60, so it will be 30. Okay, and all I'm really doing is just solving these equations. Okay, so if I let x equals 10, I can solve for y, and y would be 40, and then I can solve for a. So 2 times 3 is 600, so 600, ooh, that's pretty big. Okay, now let's try 30 here. And 30, if I had 30 for x, then I'm going to have 60 total, and I'll have 40 left over, so I've divided by 2 is going to be equal to 20. Oh, 600 again. And you can see the pattern here. Now, if I do this one 40, this will be 10, this will be 400. Okay, and what this plot looks like, if I put x on the bottom and area on the sides, you can see I'm only putting one variable here. If I put x on the bottom, here's 10, 20, 30, 40, I'm going to get a maximum of 600, 600, and 400, and 400. And there it is. There is the data. So the other piece of information, the other equation here, is that we want this point. That's the point we want. We want the maximum area. That's what we're asking for. Maximize the area. So what can you tell me about this point? Well, you can say that dA by dx is equal to 0. There is your third equation. And now you can solve the problem. Okay, so what you have to do is you substitute this equation into here, you get a relationship for area as a function of x, you take the derivative of it, you set it equal to 0, and solve your equation. But those are the 3 equations that you usually do to solve a max-min problem, because usually it's just an open-ended problem, but the last one is you're going to set the derivative equal to 0. That makes it a maximum minimum problem.